to make a table of values. You just put in x's and get out y's and see what happens. Okay, so if we've never graphed sine or cosine before, we could go through and just pick a whole bunch of x's to put into sine x and get out outputs to graph. So we're going to do that. Now notice my table of values, instead of x and y, I'm labeling it theta and sine theta. So I'm choosing angles for which I'm going to calculate the sine of that angle, and that is going to be my y value on my graph, my up and down. I have chosen, you can see, angles from the unit circle because it's really easy for us to get their sine values. On the unit circle, sine is just equal to the y-coordinate, right? So we'll be able to just go around your unit circle and get those y's. But I really could have picked any angles that I wanted. Like I could do the sine of every degree if I wanted to. Sine of 1 degree, sine of 2 degrees, sine of 3 degrees, and then I would have 360 points to plot before I got around the circle. Okay, but I just chose to do these because they're easy for us. So you guys help me out. Look at your unit circles. What is the sine of 0? 0. What is the sine of pi over 6? 1/2, which I'm going to do some of these as decimals so we can think about like where they would plot, right? What is the sine of pi fourths? Radical 2 over 2, which yesterday in war we talked about that was like 0.7. What is the sine of pi over 3? Radical 3 over 2, which we said was 0.87, and just for graphing purposes, I'm going to round that up to 0.9. And then the sine of pi halves. 1. Okay, can you imagine this, thinking about your unit circle? You just went from 0 degree angle to the 90 degree angle, and you're going on this outer portion of that circle, so isn't your y value increasing because your point is moving up as you go around? Okay, so now you're thinking, okay, I'm going to start doing the angles in the second quadrant. What's going to happen to your y value? It's going to start going back down, right? And it's going to be like symmetrical to what happened in quadrant 1. So when we get to 2 pi thirds, that's the square root of 3 over 2, which is 0.9. And then square root 2 over 2 is 0.7. And sine of pi 6 is 1/2, 0.5. And then we get to the sine of pi, that's 0. So we just went through the first 2 quadrants, looking at our sine values, which were our y's. And if we're like walking on that circle, don't we have to climb up until we hit pi over 2? And then we go down until we hit pi? What can you expect about your sines in quadrants 3 and 4? They're going to be negative. So they're going to drop, your points are now going to drop below the x-axis. And notice over here, I decided like, okay, we're going to start getting the point of what's happening. So I'm not doing the pi thirds or the pi 6 angles anymore, so I don't have to plot all the points. Sine of 5 pi fourths is going to be negative square root 2 over 2, so negative 0.7. Then we'll be at negative 1, negative 0.7, and sine of 2 pi, we're back to 0. Those are coterminal angles, so we're back to 0. So we just went through all the quadrants. We had to go up to 1, then we had to come down to 0. And we had to go down to negative 1, and we had to come up to 0. So what that ends up looking like on our graph, if I start plotting those points, and I'll give you a graph very similar to this here in a little bit, my y-axis is going from negative 1 to 1, because those are the types of outputs that I'm seeing. And then on my x-axis, these are the quadrantal angles. So here's pi halves, pi, 3 pi halves, and 2 pi. So if I was plotting that first point 0, 0, that would be at the origin. Pi 6, 1/2 would be something like right here. And pi fourths 0.7 would be something right here. And pi thirds 0.9 would probably be something right here. And then pi halves 1 right there. And then I am now in those second quadrant ones. So 2/3 pi is 0.9, 3 pi fourths is 0.7, 5 pi 6 is 1/2. That one may be a little off. And I'm at pi 0. So you can start to see, that one's probably moved over a little bit, right? You can start to see the makings of that wave that I showed you the day we did trig. Now the rest of the wave is going to be the part of the wave that sits below the horizontal axis, because now in quadrants 3 and quadrant 4, my sine values become negative. So 5 pi fourths is negative 0.7, and then 3 pi halves is negative 1, 7 pi fourths is negative 0.7, and I'm back to 0. So there's my wave. Now we're going to talk about that. Later on we're going to give that a name. That's called one period, where like we have to go all the way up and down, and then all the way down and then back up to 0. And then we could just copy this whole piece and then paste it right here. And it would just be a continuous wave, right? So like the graph really keeps going and repeats itself. Because what are you really doing? You're just going around the circle once, and then you go around the circle again, and around the circle, and around the circle, but I'm stuck on that like merry-go-round, right? There's nowhere else for me to go. I'm going to keep getting the same sine values, stuck between negative 1 and 1. Okay, so I'm going to give you a little slip of paper, and this stuff you're going to want to do in your notes. You can do the tables in your notes if you want. But this would be like intro to sine and cosine graphs. So each person is going to get a little slip that has 2 little graphs. Now, if you want to make your own graph, you're welcome to do so. You don't have to use mine. Notice that in these tables, I have chosen a very small selection of angles. So I'm no longer going to do all the angles around the unit circle. And the angles that I chose for my table of values for sine, if you look at my inputs, they're what we would call the quadrantal angles. 0, pi halves, pi, 3 pi halves, and back to 2 pi. So let's make a table of values in our notes so we know where these come from. And then we've already actually done these on the unit circle, so I'm going to kind of go and fill them in. The sine of 0 we said was 0. Pi halves was 1. Pi was 0. 2 pi halves was negative 1, and 2 pi was 0. So I'm skipping all those like in-between angles between the quadrantals that give us like the extra points on our wave. But when you graph next week for me the sines and the cosines, I'm going to want to see what I call 5 critical points, and they're essentially these angles. They represent points on the midline of your graph and points that are maximums and minimums. So go ahead and plot those on one of the coordinate planes or draw your own. Remember, these things are the quadrantal angles. So the first one that's labeled is pi halves. I know it's a little hard to read. So that one would go up to 1. Pi is at 0. 3 pi halves is at negative 1. And 2 pi is at 0. After doing the warm-up, we should be convinced that we get that like gradual wave shape, and nice and smooth and curved. So just make sure when you're drawing these, you draw smooth curves, not zigzags. So when you like come to a minimum or maximum, don't go straight to it. You're going to drop fast, and then you're going to slow down, round it out, and turn. Okay, so they should be nice and round, not zigzags. Feel free if you want to like add in like how it really continues on, right? So if you want to like make a note to yourself, like this continues. We're really going to be focused on those like 1 periods, which I'll name the period here in a little bit, but like that 1 section, and then we can just like copy and paste that everywhere. Okay, will you and your group members do the same thing for cosine? So I'm going to use the same inputs, quadrantals. And you can use your unit circles if you want. Hello, Campbell. Thank you. Okay, so fill out that table of values. Check in with your Podmates, are you getting the same answers? What are you looking at around the unit circle to do cosines? The x's. So I'm looking at my quadrantals. I'm going to go 1, 0, negative 1, 0, back to 1. 1, 0, negative 1, 0, 1. Which means your graph is going to look a little bit different. When you plot that first point, 0, 1, you're going to go 0 left or right and 1 up. So you don't start at the origin, you start at your maximum. And then pi halves is going to be at 0, pi is at negative 1, back to 0, and up to 1. Now, cosine is one of those graphs where this one's easy for people to kind of like not pay attention to ends of the graph. Remember that those 2 points that are at positive 1, that's like actually a maximum, so it's turning to go back down on the other side of that. So when you're drawing it, make sure you draw it so it's like rounding down, because this is really like a turning point. Okay, so it should be round. You don't want to draw it so it just like comes straight up to that. Then it looks like it's a parabola and it's going up forever. Okay, so you want to turn it. Okay, and if you want to draw more parts to the cosine, you can. Now, eventually on Monday, we'll be graphing these sines and cosines. So it will depend on, like what your function says. Does it say sine? Does it say cosine? As to which one of these graphs you're going to draw. And you'll need to be responsible for like what their parent graph looks like. Like where does it start? Does it start at 0, 0 or does it start at 1, 0? Okay, those are questions that we'll need to be able to answer. I'll just share with you really quickly the two like little silly ways that I remember which graph is which. And these are things that like we did when I was in high school. So when I was in high school, my teacher talking about sine always said, mountain high, valley low. Okay, so when I think about graphing sine, I know I have to get a full mountain and a full valley. So it has to start at the midline. Okay, it starts in the middle. When we were graphing cosines, we always thought about cosine starts with the CO, and it looks, this little part, looks like an ice cream cone. Starts with the CO. Yum, right? So those are like super silly, but that's kind of like how I remember what my graph is going to look like, which one. Because like they really look very similar. They're just at different places. Okay. This slide I'll kind of go through pretty quickly, but if you're curious more about like how these graphs came to be or why they're waves, go ahead and Google sine, cosine, unit circle, graphs. You'll get all kinds of animations or videos you can watch. I like this one. You see a unit circle over on the left, and the green is like the angle value, so you're just going around all 360 degrees or 2 pi radians. And then notice that it's building those triangles that are part of our bow ties. So it's always going back to the horizontal x-axis. And it's measuring that red line, which is y. And that on the unit circle would be sine. So then it's plotting the height of y, or the value of y, as our output on the graph. Okay? And then, like if you keep going around, then you just keep getting that same thing. So this would really just keep going forever and forever. It's just an extra rotation. And then similarly, there's one for cosine. Notice in this one, the animation is slightly different because as the angle goes around, it is really measuring, and I don't like this because it then looks like the hourglasses that you're not supposed to be drawing, but it's measuring the horizontal distance on the unit circle, like what is the x value, and we know that that's cosine. So our input is still the green angle for cosine, and our output is the x-coordinate from the unit circle. So it's kind of like our output x is our new y, because that's what we're graphing up and down on the coordinate plane. But you can see lots of animations like that or watch videos. So if you're like, I'm really interested in this whole thing, go ahead and Google those things. Okay. Now on to some other stuff. Amplitudes. Amplitude is a word we're going to say a lot next week. And it's important that you understand what an amplitude is. Amplitude is defined as half the distance, half the vertical distance, between the min and max. So remember, we're talking about these wave shapes. Every wave has a minimum and a maximum point. Low part of the wave, high part of the wave. One thing I would stress in the definition, as I'm like studying and making sure I understand an amplitude, is the fact that the amplitude is only half of the distance between the min and the max. So when you're trying to like see an amplitude on a graph, you don't actually want to do like what's the distance between the min and the max. If you did that, you would have to divide it by 2. You're really looking at like what's the distance from the middle of the graph to the maximum, or the middle of the graph to the minimum. So I like to do a little visual here. If you're a more visual person, you can draw yourself a visual version of the definition of amplitude. I'm going to draw a sine function here, so I'm going to go mountain high, valley low from my origin. Okay, mountain high, valley low, and I'm going to keep going because sine really does continue forever. Left and right has to remain all real numbers. Okay, so I could identify that there are mins and maxes for my waves, right? Like here's the maximum point. And then here's the minimum. But I'll also often refer when graphing to this line in the middle, which happens to be our horizontal axis right now. Of course, if we have like some vertical shifts for our graph, if we move it up or down, it will change. But I often call that the midline. Like it's the middle of the graph, right? It cuts that in half. And so that's where we see our 2 amplitudes. We have one amplitude from the midline to the maximum. So there's an amplitude. And technically, in the height of the graph, there's a second amplitude from the midline to the minimum. So remember the amplitude is only half of that distance from min to max. There's 2 amplitudes in there. And we're going to use this next week to help us do our graphs. Okay, the next vocab word that we're going to be saying a lot is period. So a period, instead of a vertical distance, is going to be a horizontal distance. And it's the horizontal distance between a point on the graph and the point where the graph begins to repeat itself. So I think we could all argue based on like the pictures of the waves that we saw last week when we did them in Desmos, that we can really take like one section of the graph and like copy and paste it right next to itself and build this whole continuous wave. So that one section of graph that we could just like copy and paste and it wouldn't overlap, it would make a whole new graph. That's going to be one period. doesn't repeat. So for this visual definition, I'm going to draw a cosine graph. So I'm going to do my ice cream cone, but I am going to continue it. Like that. That's a cosine graph. If I just looked at it, I would think it was a cosine because on the vertical axis it starts at its maximum. So if I pick that point, which for a lot of people would be very common, if you were going from a graph to an equation, you would pick the point that's on the vertical axis. So I might pick this point up here as my start point. And then think about like how long until I would start retracing. Well, here I'm decreasing. That's all brand new. And then I hit my minimum. And I start increasing. I'm hitting the same y values, but I wasn't increasing. I was decreasing before. So these are all new. But once I get right back up to that maximum, now I would be going the same route I already took, right? So I'm like repeating myself. So this piece right here, this is one period of y equals cosine x. Okay. In that little section. If I clipped it on the ends and just copy and pasted it, would build that nice wave for me. Can you look at that wave and see a different graph anywhere? It could be a sine. Yeah, so remember sine, like I always remember sine as a mountain high and a valley low, so I need a whole mountain and I need a whole valley to be a sine graph. So I have enough right here. If I started right here, shifted left, I would have a mountain high and a valley low. And this distance right here, this is one period of y equals sine x. So really every cosine graph could be rewritten as a sine graph, and every sine graph could be rewritten as a cosine graph. The big difference is there's some kind of like horizontal phase shift, right? It has to be moved or translated. And you might even have said, well, what about some other ways? Like I could really pick any other point that I wanted to. And one that we'll see when we get to graphing next week is, you know, like for my red one, I went max to max. Could I have one period min to min? Yeah. This one is one period of y equals, it's my ice cream cone flipped over. So negative cosine x. And we could try to find one that was y equals negative sine x, where we did valley low, then mountain high. So that's like the interesting things. When I give you those two parent graphs, we really have 4 possible graphs to go off of, the originals and the reflections. Okay, so next up we're going to start talking about, okay, well, what about those, like the one Logan pointed out where he thought it looked like a sine graph, but it was just shifted. Okay, where do those shifts come from? Or what if my wave is taller than the parent graph? Or what if, like a slinky, I stretch it out horizontally or shrink it horizontally? Where do those things come from in our equation? They come from our general equation. So I would make sure I get these 2 equations written down. Okay, y equals a times sine of bx minus c, and then a plus d, and y equals a times cosine. Same thing, quantity bx minus c plus d. If you can take a trip down memory lane to Algebra 2 and first semester for us, I mean, these are essentially going to start describing the same things we've always been doing, but we've been doing them with A, H's, and K's. So A's were responsible for vertical stretches and shrinks if they were outside of the function like this. And so that would make our wave taller or shorter. Previously, A's were responsible for horizontal stretches and shrinks if they were inside the function with the x. So that in like our wave would like make it take longer to repeat or less time to repeat, like it could go really fast. What I like about trig is because this happens a lot, the horizontal stretching and shrinking, that they gave it its own letter. So now you have a B for that. That's in front of the X. So that's going to be your horizontal stretch and shrinks. And then we used to have an H and a K, left and right, up and down. And essentially that's kind of what our C and our D does. D is going to be just like K. But I'll talk about here in just a minute. C you have to be really careful with if B is something other than 1. Because the horizontal stretch or shrink is then affecting your left-right shift. So we'll talk about that one here in just a little bit. But it is essentially kind of like your H. Okay. So let's jot these things down. If you're given an equation when there are some extra numbers, it's not just sine x or cosine x, then your amplitude is the absolute value of A. So make a note to yourself if you want to write it out in words in your notes, you can. Amplitude is always positive. Okay, it's a distance, so distance would be positive. We use absolute value. If you happen to have a negative A, I mean, that's possible. It's not going to affect your amplitude. Your amplitude would still be the absolute value of A, but it will reflect your graph. So I kind of talked about that when we looked at the definition of a period, right? Instead of like a sine graph being mountain high, valley low, if we reflect it over the x-axis, it's going to be valley low, mountain high. So you can reflect those waves. Okay, the period, remember that's your horizontal distance. So your horizontal distance, like a slinky, is going to be affected by the horizontal stretch or shrink. So that would be your B value, the thing that's getting multiplied by the x inside the function. Okay, notice bx and bx. The parent graph, if you look back at your little graphs, they have periods of 2 pi. Okay, so that's where we're getting this 2 pi from. That's from the parent graph. But if we stretch and shrink it, then we'll have to divide it by b. Okay, so do you remember like back when we did horizontal stretches and shrinks and we didn't do them a whole lot? Like if you horizontally stretched it by a factor of 4, you put a 1/4 in here. And if you were shrinking it by 1/4, you put a 4, you use the reciprocal. So that's why we're dividing it by b instead of multiplying it. And I suppose technically that should be an absolute value of b. If you were ever to have a negative b, you would only use the positive version of that because period is another distance. Okay, here's that part about C that I was talking about. You have to be careful with C. C is like our H. It's going to help us move left and right. But the one thing you have to be careful of, if B is not equal to 1, you have to factor out the B to really figure out what your left-right movement is. So we did this a few times in Algebra 2 and maybe first semester, where if you have like some bx minus c and b is not 1, then you don't really know what this left-right shift is until you factor out the b. You have to have a 1x right there in order to say like that's your left-right movement. So we took out a b from bx, but then we have to take out a b from c, and you're like, well, how do I do that? Well, it's just c over b. So that if I redistribute, b times 1x would be bx, and b times c over b would just be c. So your horizontal shift is really c over b. And this is also a good spot for you to make a note. C always looks like the opposite of what it is in the equation. It's just like H. I used to always say that about H as well. Notice that in the general form for the equation, it's supposed to be minus C. So if you put a positive C in there, it looks like a minus. And if you put a negative C in there, then it's minus a negative, which looks like a positive. So you'll have to remember when you're pulling out the C that it always looks like the opposite of what it is. Okay, and And that'll get a few of us multiple times. D is responsible for the vertical shifting. So that's like your up, down. That's your K. And there's nothing really special to know about that. The other thing that I'm going to ask you to do on your homework tonight is put the horizontal and the vertical shifts together as a starting point for your frame. Now this part doesn't mean anything to you right now. But I just want to have it in our notes so that if we're ever, like after Monday, flipping back to this day and we know about the frame and the starting points, that we're aware of what we mean here. So I'll ask you to identify the horizontal and vertical phase shift for the starting point. So you just put together the C over B and that'll be your new starting point. Okay, so we'll do a couple of quick examples so you can see like what things you'll be expected to do on your homework. And then I do want to hand back your quizzes from yesterday, and you'll have quiz corrections to go along with this homework assignment, which is not a bad homework assignment. So here are some examples. I put both of these in your notes, so you can look back and see how we did this. But essentially, I think on most of the homework, this is what I'm going to ask you to do. Identify the amplitude, the period, and the starting point. Like that's our main goal today, is can we get those things figured out? On Monday, we'll use all three of those things to create what we call the frame or the window for our graph. So we're going to start with y equals 4 sine 6x. And I would say this one is a moderately easy one. Now, if you're beginners to trig graphs, it might help you to write the general form above the equation so that you can figure out what's A, B, C, and D. It's pretty clear to see A is 4, B is 6. What's C and D? 0, because C is being subtracted and D is being added. We must be using the additive identity, which is 0. You can add or subtract 0 from anything, and it's the same thing. Okay. If it was a 1, we would actually see it, right? Okay. So they must be 0. So now I'm ready to go for amplitude, period, and starting point. Okay, amplitude. For the sake of my notes, I'm going to say it's the absolute value of A or the absolute value of 4. That is 4. I'm going to guess most of you probably don't need to write down the absolute value part, right? But you would want to be really careful if that were negative, that you give me the positive value. Oops. Let's X out. How about that? Okay, period. We're going to do 2 pi over 6. And really, like the absolute value of 6, always make sure that's positive. What would you do with 2 pi over 6? Reduce it. 2/6 is really 1/3, right? We want it to be like reduced nicely. So this is pi over 3. Okay. Now I'm going to demonstrate what that would mean visually. This is a sine graph. So normally it would go mountain high, valley low. And it would take 2 pi to do that, right? Well, now we're saying we're going to do mountain high, valley low, and we're going to get it done in pi over 3. So it's going to shrink horizontally. Here's pi over 3 compared to 2 pi, right? A third pi compared to 2 pi. And in this little section, I'm going to do mountain high, valley low. And then in the next pi over 3, I'm going to do mountain high, valley low. So in that long stretch of 2 pi, I'd really get 6 of those waves in. So we're horizontally shrinking it. Let's see, starting point. If C and D are 0, this is easy, right? It's just 0, 0. Because C over B, if C is 0, it's going to be 0. D is 0. So there is no left-right shifting. Okay, one more. Y equals the cosine of 1/2 x minus pi fourths plus 2. Again, good idea if you're like not sure which values to use. You can always write. Oops, that's a minus C. You can always write above what the general form looks like. D sometimes shows up at the beginning. Like it could say like 2 plus the cosine. So if you have one number that's being added or subtracted, that's your D. What's A? Now it's being multiplied by cosine, so you would use the multiplicative identity, which is 1, not 0, right? If it was 0, then that would be a very uninteresting graph. It wouldn't be a wave, it would be a horizontal line. Okay. So A is 1, that means our amplitude is 1. For our period, we're going to do 2 pi because that's the period for the parent graph if you look at your graph we did, divided by B, which B is 1/2. Okay, you got to be really careful here. You're dividing by 1/2, which is the same as multiplying by 2. So I'm going to get a lot of people on a lot of quizzes and tests who lose a point because they're going to say 1 pi. They're doing 2 pi times 1/2. But it's 2 pi divided by 1/2. So this is really 2 pi times 2, which is 4 pi. So what that means for this one is the cosine, starting at the max, drop all the way to the min, come all the way up to the max. It took 2 pi to do that. Now it takes double that time. So in that 2 pi, I only get from my max to my min. And then I have to have a whole nother 2 pi over here to get up to my max. So now my graph is horizontally stretched. Okay, starting point. Now we got some interesting C's and D's, right? C over B is the one we want to work on. Okay, careful here. What is C? In the equation. What's the value of C? Pi over 4. And Aiden is saying positive, right? Because it looks like a negative, it is a positive. You must put in a positive C value. So that's pi over 4. And B we already used for our period. That's divide by 1/2. We already know dividing by 1/2 is multiplying by 2. 2 over 4 is 1/2. So this is pi over 2. Okay, so there's 2 things you got to be really careful of with C over B. Number 1, C looks like the opposite of what it is. If it looks positive, it's negative. If it looks negative, it's positive. And then divide, be careful if you're dividing by a fraction. Okay. Then you're multiplying by its reciprocal. And D, of course, is just 2. So what this means is like when I start that like max to min to max, like my ice cream cone, my graph of my cosine, before I graph it, I'm going to move my window. I'm going to go right pi over 2, and I'm going to go up 2. And then I'm going to draw my ice cream cone for my cosine graph. Okay, so your homework assignment is this one on the gold sheet, page 306. If you've been confused because we added a day for the quiz, kind of mark this on your gold sheet for me. When it says 529 and then it has the x3s, that means by 3s. So you're doing 5, 8, 11, 14. So really 5 through 29 by 3s is not a lot of problems. Okay. And what I want you to really do is do what we did in the examples. Okay. State the amplitude, the period, and the starting point. If it asks you to graph or do anything else, You don't know how to do that yet. We're just focused on can we get these things, periods, amplitudes, and starting points.